In this video, we'll be looking at the detailed design process from the perspective of hardware, and later on we'll look at the perspective of software as well. Many of our engineering systems that we'll be working with will have some sort of hardware design or the sort of off-the-shelf or modified off-the-shelf hardware that we can actually use within our system. And so hardware is a very important thing. Now, whether that hardware be some computer hardware or whether it be pylons that hold up a bridge, hardware is hardware, and it's important that this hardware actually meets the needs and requirements of the system and will actually deliver on those. In our detailed design phase, we'll be basically guided by the sort of framework, the top level framework that we had in our preliminary design phase. That gives us a big picture view of what we're trying to achieve, and then the hardware that we'll be looking at here is specifying in full all the subsystems and developing them and making sure all the parameters and design parameters actually meet the specifications. So if we thought of this electronic hardware level, for example, as a IC designer, we're probably going to have requirements specifying what it actually needs to do, but also the sort of power constraints associated with it, sort of processing capability that's associated with it, the size that's associated with it, and the heat dissipation that's associated with it. And so all of those sort of constraints need to be taken into account. Likewise, anything else we design, for example, we design a bridge, we'll be talking about the static loading, the dynamic loading, the seismic activity that this needs to be able to withstand, whether the bridge is actually a bridge that actually moves up and down to allow boats to pass through into a harbour or something, for example. A whole range of different constraints. And the main constraints about how this bridge will actually be supported. Will it be pylons? Will it be a suspension bridge? Who knows what it will be? Well, those sort of big level things will be detailed in the preliminary design stage. Here we're getting down to the nuts and bolts, sometimes literally, of how these things are going to be built and held together. One thing that we can remember is this is an iterative process as well. So we start our process, we perform analysis and work out what we want and how we can do it. We perform synthesis, whether it be simulation or prototyping and things like that, and then we perform evaluation based on that. And if the evaluation is satisfactory, we can finish the process. Otherwise, we'll go around and perform further analysis, work out what we need to change, what we can improve, perform synthesis once again, and perform evaluation once again, and we go through this loop. Now remember, we had different options of how we acquire our hardware. It could be commercial off the shelf, could be modified commercial off the shelf if we find something that's a close fit and we can modify it to suit, or it might be developmental. We'll need to work out how to integrate all these together and ensure that they actually mesh together, that they're not using conflicting standards or conflicting protocols and things like that. We may need some things in there to actually translate information between the different modules that we're using or whatever it may be. One place that this may cause issues is if we're getting components from different countries and some are in a metric form and some in an imperial form. And so our holes, for example, that we want to bolt things to might not line up together. So we might need to develop some plates that form as adapters or something like that, or we may have to drill some additional holes, which would make something modified COTS, for example. We could do that on a drill press or on a water jet or on a milling machine or something like that to ensure that we can integrate our different components together. We also have a whole range of tools in computer-aided engineering and computer-aided design that enable us to perform the design of software and of design of hardware as well. So here's a few benefits these CAD packages provide to us as designers. One thing is, when we see the complete design laid out, we can actually see what's complete, what's not complete, what still needs to be done. They also allow us to avoid costly manufacturing errors of when we send something out to manufacturing and then it doesn't quite fit or doesn't quite meet the specifications or requirements. Now, in the early days when I was starting out doing lots of mechanical design, I used to use this more trial and error sort of approach, and invariably things didn't work and it took the second or third try to actually get something to fully fit together. If that was fully CAD'd up to begin with, a lot of those errors could have been mitigated and I wouldn't have had to get the Dremel out and remove little bits and modify little bits to actually make things fit together. It would have been a whole lot easier to actually ensure the design actually meshed together properly, and if that design meshed together properly, we can be more confident. We can also better understand how the system will perform across its life cycle. So we can do modeling here about mean time to failure and when things will fail, and be able to assess what components have the most stress placed upon them and what are most likely to fail. And so we can work out what spare parts are required and how those spare parts can be replaced and maintained and things like that. We also get to see how all those components fit together. It's very hard sometimes modeling these complex systems with our hands or with bits of paper and things like that. In CAD, we can actually model it fully. And we can also model the sort of forces and other things that are placed on there where we see how they behave under external stimuli. So here we're modeling an air turbine, for example, and we're seeing how temperature can change through there, where the airflow will form with these sort of CAD packages. We can also do this not just in the mechanical field, but in the electrical field as well. And so very rarely would we go and build a circuit without actually having drawn up a schematic associated with it. And with these schematics, we can model the current flow and the voltage drops across various components. We can also go through when we're creating our circuit boards and actually fully lay out the circuit board and create mechanical models of those circuit boards to see how they'll fit within enclosures and things like that. And we can create heat models of them as well, how heat will be dissipated through various sections, particularly the parts that are generating more heat, things like our voltage regulators or our switching components, for example. And so we can also do this at an assembly level as well. Our system might fit into a larger system and we need to work out where our wires and things will be routed around. We can very easily do this with layout software to allow us to ensure that this is done in a structured and recorded way and in a repeatable way as well, not just putting things wherever it just seems to fit. And of course we want to document this process. If we don't document it, we'll invariably forget things, and we won't be able to do this in a repeatable fashion and won't have the proof that our design is actually working and is meeting the specifications. And so we need to ensure everything's documented, and we'd be including things like version control in here so we can look at previous versions and look at changes from versions, why we've made those changes and how those changes will affect not just the components and then the subsystem we're working on, but the overall system as a whole.